Welcome, everybody. Welcome tonight to this first day of Pint of Science online, the edition of 2020. Very weird year, and since also in this case we had to take a strange measurement to bring you Pint of Science. My name is Michele. I will be your host for tonight, and with me we have also Anna. Hi, Anna. How are you?
Hi, how are you?
All good. All good. Excited for today, first day
Yes, me
of
too.
this Pint of Science Festival 2020, which is going to be a bit weird, but nonetheless probably very, very fun. And so today we are going to talk about something really weird. We created a sort of strange topic for tonight. We try to mix out of our general stream and subjects in different ways. And the title of today is "Recycling Stories from the Earth to Space." And today we have two very, very nice speakers with us. But before to introduce them, I just want to remember to all our audience how you can interact with us. You can just write in the comment sections. I don't know if you are in Facebook or in YouTube. It's exactly the same. You just write your comments and your questions. There will be also a Q&A sessions after each speak. And we can discuss about this, and you can ask whatever you want to our guests. So we will have two different topics tonight. In the middle, just a small break to let everybody the chance to fill your glass of beer, because of course it's not Pint of Science without beer. And
We bring the science, but they have to do that part, huh?
Of course, we bring the science, but the beer is your stuff, guys. So without waste other time, I want just to introduce our two speakers for tonight, both from KU Leuven. Actually, we have Anastasia Papagelou. Hello, Anastasia. How are you?
Hi, everyone. I'm good. Glad to be here. Hi.
And you are a PhD in researcher in KU Leuven Earth and Environmental Science Department.
Exactly.
And today you are going to speak about, I would just say that you're going to speak about phosphorus. Just to be very, very generic, because I think that it's a very interesting topic and it's a strange angle to see it, but still very, very exciting. And with her, which will be our second speaker, we have Marie van de Sande.
Hello.
Hi, Marie.
Hi.
How are you?
I'm fine. Happy to be here.
And Marie, actually, you are a postdoc researcher in KU Leuven Institute of Astronomy.
Mm-hmm.
And also with you, we are going to talk about a kind of waste. But in a certain way, the title of your presentation is Recycling Stars. And I'm super excited about that. I have to say that it's very, very, both are very interesting topics, and I cannot wait to hear about that. So before we start, I just want to say to our audience that after the presentation of Anastasia, there will be, again, a small break, and then we have the presentation of Marie. Of course, you have the time to go to take some beers and then come back. But after each presentation, there will be a Q&A session. So shoot your questions, and you can also shoot during the presentation if you want. But usually we prefer to have all the questions at the end, so it's even easier to reply to all of them. So for now, I just want to say for now hello to Marie. So we are going to see you later. Thank you so much.
See you later.
And Anastasia, so when you are ready, we can start. I think that the audience is ready, is very hot, and is very ready to listen to you. So when your presentation are ready, we can just leave you the stage and you can start.
I'm good.
Okay, perfect. So I will just leave with Anna, and the stage is yours.
Okay, so imagine you're sitting around a table full of friends and family, and you're sharing dinner, passing around plates full of delicious food. Isn't there always one person that interrupts the natural flow of food? You know, the passing of the plate of potatoes from one person to the next and then to the next. Well, in my family, it's let's call him my Uncle Bob. This person that keeps the plate with the crispy, delicious potatoes, and instead of serving himself, he's just chatting to someone else. And then the chatting is becoming so heated that he even leaves the plate in front of them to gesture with both hands while you're sitting 2 people further down and the potatoes are getting cold. Well, we humans are the Uncle Bob of the phosphorus cycle on Earth. Now, phosphorus is essential for all life. Is a valuable resource, a great gift. But what we do is that we are wasting and misusing it. Why are we doing it? And what is it actually that we can do better? So my name is Anastasia Papangelou, and I'm doing my PhD at the Department of Earth and Environmental Sciences at KU-Leuven, as Michele just said. I have been studying the nutrient flows in Brussels and in Belgium, and especially in the food system. And today I'll take you on a journey to follow one of those nutrients, and this is phosphorus. So in the next few minutes, I promise I'll keep it very short. I want to give you an overview of why we care about phosphorus, why this little guy is so important, and then what is it that we do wrong and what we can do better. So a little disclaimer before we continue is that after all these years, me and phosphorus are in quite friendly terms. So maybe I will be calling him P or just writing P. Don't worry, it's always going to be phosphorus. Okay, I hope you're ready, so let's start. I want you to take a second first and think of the last time you thought about phosphorus or the last time you heard phosphorus. What is it that you know about it? I will actually give you a couple of seconds to do it. I will get off the screen for a while. Okay, I hope you all thought very hard. So you may have thought that phosphorus is a chemical element, and maybe you remember the periodic table from your school or your studies, or maybe you even remember the place of phosphorus on the element. So phosphorus, I will call it, or we call it a nutrient. In my field, we call it nutrient a lot, but it's not one of these macronutrients that we are discussing. We're discussing, for example, human nutrition, like carbohydrates or proteins. Nonetheless, neither of those macronutrients or anything else could be formed without phosphorus. So phosphorus is like for the cells, it's like the currency for their energy currency, and it's an important currency. Think a small golden coin, right? Not just a paper 5 euro bill. So the cell doesn't need a lot of it, but just by, for example, breaking a bond of this phosphorus, it can release enough energy to then put together these molecules of the macronutrients that it needs to feed itself. And at the same time, phosphorus is also a building block of our bones and of our teeth. And our bones and our teeth, they contain more than 10% of their weight. More of 10% of their weight is actually phosphorus. So that means that we need more phosphorus as we grow up, but not so much anymore when we are adults. But things are a bit different for the plants. So the plants need a steady source of phosphorus in order to grow and in order to thrive and to produce our food, that then this food is going to be the food for us humans and for animals. So if we take our phosphorus from our food, where do the plants take it from? Well, the obvious answer is from the soil, right? And how does it end up there in the soil? So one way is this, let's say, long and slow process of weathering from the rocks, and then through erosion and runoff, it comes down to the soil, and it ends up maybe in the water and in the sediments. So this is, as I said, a long, slow process. But in there is also a smaller little cycle that is a bit more lively and a bit more relevant, let's say, for what we see here. Can you guess what it is? And I'm pretty sure that if you know me a bit, you know what it involves. It involves poo. So this is, let's say, the fastest and the main mechanism to circulate phosphorus in the earth. And it's really because we don't use it as much as we saw. So when we eat it, quite a lot of it is actually lives in our body with our excrements. And the earth, or let's say the nature, has really found some extraordinary ways to make sure that this cycle is always working well and phosphorus together with other nutrients is circulating. Tell me, have you ever been on holidays and then came back to your car that you had left under an olive tree or whatever tree, and you found a goat on top of it? I don't know, maybe it's just too Greek thing or too Mediterranean thing, but it happens a lot. And this is then what it happens. So the little goat comes there and uses your car as its little, this kitchen ladder that they have 2 steps to reach on the high leaves on the trees. And when it eats the leaves on the trees, it takes all the nutrients that it's in there, and then it actually transfers it all the way down back to the soil with its poo. With giraffe, it's the same, but she's tall enough and she doesn't need the little ladder. And one of my favorite is also the whales. So the whales, these extraordinary creatures, what they are doing is they are doing kind of the other direction. So they go and they feed deep into the ocean where not a lot of other animals can actually reach. So they go and they feed there, and they go up to the surface, and they take a big it's really pink dump. And like this, they spread the nutrients and the phosphorus all around for all the other creatures that they live up there in the surface. So this is what we have been imitating when we started cultivating the land. We started using cow's poo or other domestic animals' poo, that it's obviously manure. We have also been using our own poo to fertilize the land, which I will call human manure from now on, because let's admit it, poo is a bit silly. And we also tried then to find, as agriculture was growing, we tried to find other ways and other sources to complement all these. First, we used guano, that it's, let's say, fossil birds' poo that we can only find in very specific places. And eventually, we found mineral, or we started using a lot of mineral fertilizers, and therefore for a while this worked greatly. So we were using more and more fertilizer, and this helped to have the green revolution and produce more and more food to feed the people. But like always, it's not only great, right? There must be a downside. The downside is that by using so much of fertilizers, and quite often not very wisely, we started polluting our rivers. So here you can see then the nutrients would be washed off from agricultural fields or other sources that we'll see later. And when they end up in waters, they do the same that they are meant to do. So they are feeding the plants there. The problem is that if the algae are so happy and they have all this food, they started growing very, very, very much, consuming all the oxygen that is there, not leaving anything else for the other creatures, and also create this shade so that the light cannot reach deeper into the waters. And it's not only about pollution. So in contrast with nitrogen, phosphorus is a mineral source, and we have to mine it, to mine phosphate rock in order to make mineral fertilizers. So now there is a debate that it's still unsolved, or it depends on how someone sees it, whether we will run out of phosphate soon or not. But the thing is that even if we say that we won't run out soon, and we have enough to go on for centuries, so we don't have any physical scarcity, the thing is that these resources are concentrated in very specific places in the world, which means that, if there is any geopolitical or economic reasons, their distribution or access on it may be hindered. And the most important thing, and then not also our access may not be hindered, but the thing is that, okay, if we have a resource that it's, let's say, even if it's not scarce, it's not infinite, right? And we have another way to do it here. Why not just care about the just distribution of this resource and use what we have already, and let this mineral, the mineral part of it, available for people or places that may be needing it most. So just to sum up, and you're very lucky that we are not in the same room, because now I would have made you take a test. We saw that phosphorus is very, very, very important, because all life depends on it, because we absolutely need it to grow food, and because being careless with it can cause problems to the environment and in generally in our future. So what we need to do is to manage phosphorus better. And what we're going to see now is what exactly are we doing now, a bit more in detail and a bit more specifically here in Belgium, and discuss a bit what we can do still better, as I said. Okay, so just to give you an idea, when we are talking about, we saw how phosphorus is in let's say, nature and agriculture. Let's see a bit how it is in our societies. So phosphorus is very intrinsically connected to food. So let's say that we have a loaf of bread in my house in Brussels. So some of this bread, unfortunately, it will go to garbage. Not very often, but some of it I will eat, and then the phosphorus in there will end up in my toilet, and there in the sewers and the wastewater treatment plant, where it will be treated, and it will be, let's say, turned into a material that it's safe to transfer, and usually we either use it for other uses or we just incinerate it and landfill the ashes. So this comes after we have the bread. So before getting to the bread, we are obviously buying it at the shop. And this shop also has some waste for itself. And this shop, there are some steps there that I just took out for the sake of simplicity. But this shop is then taking its flour and its wheat and everything from the crops that we grow here in Belgium. But this wheat is not only there to make my bread, right? It's also there to feed cows and livestock. And since we have so many cows and so much livestock, they are also producing manure. And so nice that we have this manure, or maybe not, we'll see, that then we can use back into the soil. And if we have too much of it, then maybe we'll burn some, or we will, let's say, treat some and try to do something else with it. So this is the very rough sketch about me and my bread. Let's scale it up a bit and put some numbers and see what happens in the whole of Belgium. So I cannot guide you through that. Okay, so if we start on the right, when you see the little city, So here we don't have anymore just a person, but we have a whole city, right? Citizens and all of us that are there and eating. And this is what we are eating. Maybe I should say that here it's the numbers are, let's say, normalized. They are scaled. It means that 100 kilotons is what comes in the country of Belgium. Yeah, this is then how all the other flows are looking. Maybe it looks a bit messy, but let me guide you through it. So we are on the right, and this is what we eat. We eat 15 kilotons of phosphorus per year, which means roughly, let's say, around half a kilogram per person. And from that, as we saw, most of it will go down in the yellow flow, and it will become either wastewater or some of the food waste that we're going to throw away. And then from the little bin here down, that it represents the waste management system. A lot of it, as you see, is getting emitted or lost, which is again what is either landfilled or what is exported, maybe to be treated somewhere else. While the little green arrows, the little green flows, some of it will make it eventually back to agriculture. So let's see. Our food then, this blue arrow that goes into the city, is coming from the industry. That it's again kind of an aggregate sector here that represents the industry, the packaging, the retail, and so on. And as you can see here, while like this little 15 flow comes out, there is a lot needed, a lot coming in order to make this possible. And again, you can see the first two blue smaller flows that are the animal and plant products that are needed, and then also how much feed is needed to feed the livestock and then go back, become manure, the little green flows that returns back to the land, the forage, the little blue flow from the grassland to the livestock that is used to feed it. And eventually also all the way to the right, the extra inputs we are putting mainly as mineral fertilizer here with the phosphorus. So by just looking at it, I hope it doesn't look too messy, but we can see already a few things of what is this journey of the phosphorus, and maybe also a bit about what is wrong. So as we can see, first of all, even though we have a small flow, let's call it flow, coming into our houses and into our cities, just to make this small flow, it's a lot going on the backstage, which we can say already that that means that maybe one of the most important things to do is to grow our food better. And I don't mean we don't do it now, but I mean if we want to manage nutrients better, it's important what we grow, what we eat, and how we grow what we eat. Or we can say that if you see the little purple flow coming out of the industry, for example, this is also losses and things that we are not reusing currently from there. So we can see what we can do for these losses, how to find a way to treat them properly so that we can reuse them, or how we can maybe revise the legislation so some of these products we can actually reuse them, and so on. So there are different things, but I will, like for today, I wanted to focus on one, and this one is our humanure. So as we saw, our humanure, it seems quite small compared to what is the manure cow, for example, and so on. But it's still interesting because first, most of it, as we saw, it's gone anyway. And second, because if you see a bit the comparative amounts, actually what we are producing in our humanure is more or less how much is coming in the system or how much we're introducing as mineral fertilizers. Of course, a little disclaimer here. I know that it's not as simple to just starting using human manure just like this. It means that it will need to be properly treated and properly monitored so that it becomes safe and also economical to use it back in agriculture. So that may mean that, okay, if we need these like new technologies and fancy processes to make the human manure into fertilizer or into something useful, maybe it will mean that we actually need so much extra energy to do that that it's not environmentally relevant anymore. So maybe yes, but it's also not necessary. I have here a small example from Brussels, for example. Again, let me walk you through it. You can see all the way to the left. It's a comparison of or the amounts of what is happening right now. So right now, the green column where it says phosphorus is how much phosphorus is recovered right now from what we call the waste flow. So both organic waste like food waste, green waste, and human manure. So this is only the green waste. And on the right side is how much net energy we are gaining now by treating the waste. And in the baseline, it is a lot because we are incinerating the organic waste. So we are getting all the heat from this energy. And there we compared two different alternatives, let's say, very, like theoretically what would become if we would instead use or reuse all the food waste, if we would digest them anaerobically and then use them in compost, and what it would happen if we would reuse all the phosphorus in the human manure, which is the third set of columns there. And the last one is what would happen if we would had both of them together. So what we see here, it's, let's see only the two in the right and in the left. So what we see in the baseline, we have almost no phosphorus, but a lot of energy recovered. And what we have on the right is a lot of phosphorus recovered, but not as much energy. So that means pretty much that there is this huge amount of phosphorus that right now is lost. But if we lose it, we might use some of the total net energy recovered from the incineration, because we're actually getting all this waste out of the incineration. Well, this is true, but also I want to say that it's different, because most of these we are losing total energy, but we are gaining a bit of electricity. So the dark blue line, that it's the electricity and not the heat, it makes a difference. And this is why, imagine, for example, if we are generating heat somewhere, it's a bit like having a heater or a fireplace in a room in your house, right? So you have it there, and the heat is going to heat the surroundings, but it's difficult then to transfer it to another room. So it's a bit of the same when you have a big incinerator, while electricity, it's kind of easier to use it directly. And also, to put a bit into perspective the numbers, this amount of phosphorus, if we regain it pretty much means that it could cover all the mineral phosphorus that is used right now in the two areas around Brussels, the two Brabant regions, while the amount of electricity is less than 3% of what of the electricity demand in the city of Brussels. So as we say, it is important, and we will need methods and treatments, but it's not necessarily only negative. And what will also mean for sure is that though we will need to change a couple of things, and a couple of important things. So there's a lot of research going on in the moment to find these new technologies, and also to rethink our waste streams and exactly what is it, what is the form of our manure and our poo. So maybe we will need to change our toilets and start using these kind of toilets that keep the poo and the pee separate, so there is no so much water involved, and it's easier to transfer them and to treat them. Or maybe we will need to bring the food production closer to the cities and closer to the concentration of these nutrients. So, but in any case, in the end, what we need to do is to basically take example of the goat that we saw before, and rethink our poo making as a gift process. So as an exchange of gifts with the earth, we take the gift of food and we are giving back the gift of nutrients to the land. Because who wants to keep food for themselves, right? Who wants to be Uncle Bob? Thank you very much, and I'm happy to hear your thoughts and your questions.
Thank you so much. Anastasia. Was really interesting, and I already have a lot of questions. So for our guest, before we start, for our audience, sorry, if you have any questions, just shoot it. And also, Marie, if you have any questions, just give me a sign, so I will jump. I will put you in the conversation. First of all, thank you, Anastasia, because it was really interesting and was a point of view that is not so obvious for everybody. So it's something that it's not very obvious for everyone, that how much is important, something like poop, that we don't really take care so much about it, but in the end is very important. I don't know if this question makes sense, but so you talk about compost, okay?
Yeah.
So, and in the very last slides, you show it a possibilities to have basically gardens gardens, or a place where actually you can have food, vegetables in the cities. But do you think what is more doable for our society, to have something more related to individual? So, for example, you showed some toilets that can sort the pee and the poo, or it's more easy to have like a huge, huge factory where you bring everything there and you treat everything, you produce phosphorus there, you recover phosphorus from there.
Yeah. Okay. So my personal opinion on that is that it's obviously easier to do things by using the infrastructure that we already have. So of course we now all have, our nice porcelain not separating toilets and our sewers. And of course we need the water to take everything away. So just, indeed, we cannot just take out all the sewers around and put new toilets and change things, like how do we do things from the one day to the other. So the transition, it has to be slower, but I still do think that we have to keep our eyes further into the future and really say that, we do want to get there, and we don't want to forget that when it's time, maybe after, when we can change maybe the sewers, or we can really rethink important laws, or, all these things, that this is where we need to go.
Okay.
Does it make sense?
I was actually wondering, in the same line, are there cities that do differently? Like your work focus in Brussels, but I was curious to know if there are other places where they have thought of this somehow farther already.
Really on implementation, I really don't think so. I wouldn't cut my hand, as we say in Greece, but I don't think so. But you can see that there is a lot of interest, right? There is also, for example, a lot of research in the Netherlands, for example, and in Amsterdam, where they are really going, they are developing these models where we go building by building, and they can see, okay, how much is produced there because we have so many inhabitants, and and maybe there is a community garden right there. Then I can send it there. So in terms of implementation, it's a big thing. So I don't think it's happening, but it's something that a lot of cities start start looking at, because it is indeed a fertilizer factory in your door.
Yeah.
Okay. So we have a first questions from the audience, and the question is phosphorus from every source safe to be recycled? Does it matter where the phosphorus is coming from? Because detergents could be environmentally harsh. That's a very good question, actually.
Yeah, exactly. So yeah, of course it matters. Let's say to that I will say first that at least in Belgium, it's really we are phasing out detergents. So I'm not sure which one was left. I think it was like for the clothes and for the household for many years now that you couldn't put phosphorus in them. And recently they also did it for dishwasher or something, But anyway, the thing is that we are phasing them out, and this is one of the reasons why we are doing we are improving in the whole of Europe in phosphorus pollution in fresh waters. The big, in terms of if it's safe to be recycled, of course, the big elephant in the room here is that when we are talking about poo, there are pathogens, and this is actually the thing that mostly we need to take care of, and other things, but yeah.
Okay. Nice. Actually, our second guest, Marie, she has a question for you. So I will just let her speak about it.
Thanks for the talk. It was very interesting. And I think I have a very basic question. Namely, how would a separating toilet work? How would you go about doing that?
Thank you for this question. I love this question. Actually, I don't even do so much about separating toilets, but I really like them. So the thing, you don't need to do anything actually. You just do your job as you know. Well, boys need to sit, which is good also for the housekeeping, if you know what I mean. And so because it is like this, I don't know if you notice. So the front part is a bit kind of flat. And it has small holes there. So when you pee, it naturally goes there and then it goes down the little holes. And when you flush, the little holes are closed. So no extra water is coming to the pee.
Okay.
And then when you're poo, then the poo goes directly back and uses, let's say, either you can have it dry, but also you can have it with a little bit of water to go there. But again, the little holes are closed, so it doesn't go in there and it doesn't dilute it.
Interesting.
Okay, it's very smart actually. It's a very simple,
I know, right?
a very simple solution, but it's very, very smart. Yeah, always the great idea are like this. So we have a question from Guillaume that is actually a kind of strange question, but he has a point. Should people be encouraged to poo in public parks?
Yeah, no, please don't, no. No. So as I said, it's we are not the little goats that we are just one living alone down a tree. We live millions together, very close to each other, on top of each other. We live in places that are, full of cement. So other rules apply. It's a bit more complicated. Let's not, copy exactly, but let's get inspired by the little goat, I will say, Guillaume.
Yeah.
Plus, you cannot wash your hands in the park. It's very important.
Yeah, totally. That's another good point. Anna, do you have any questions?
No, I was wondering about if other countries or the other cities do different things, and I was also wondering if there are other nutrients. Is only phosphorus, or this is the example that you use to make us understand?
Exactly, it's the example, and it's also, let's say, the thing with phosphorus. As I said, it's interesting because it's also, let's call it a scarce resource, right? So nitrogen, you have it in the air. First of all, and also for nitrogen, the plants themselves, they have a way to fixate it and transform it and take it up. So from the air through the bacteria, through some bacteria in the roots directly to the plant. But for phosphorus, it's not like this. Phosphorus is less mobile. And also, as I said, a scarce resource. So we should be careful how we treat it. And this is why I presented it here. And this is why actually I do pay special attention to it on my PhD. I do have a favorite nutrient, it's phosphorus.
Okay. So we have a question from Renata. Do you have an estimate of how much of the P that can be recycled could contribute to the demand of P in the EU? The critical raw materials list has just been updated, and P is still furthering high in there. Thank you for the great presentation.
Thank you, Renata. I don't, on the top of my hand, I have to admit, but there are studies on the European level. I have to say I cannot tell from the top of my head. What I can say, maybe more or less, is that maybe in other countries, not like Belgium, that we have so much because of manure. Let's say the input from mineral fertilizers, it's bigger. So maybe then the human manure is smaller in comparison to the others. But there's still potential, and this is why also like research is going on all over the world. I hope that was an answer enough.
Yeah, it was. We have still a bit of time, and actually I have a question. So we were talking about mainly poop because I don't know, it's always in the end an interesting topic somehow. I don't know how, but you were also talking about food waste, and I live in Brussels, so I already have we already have a system to collect the food waste. But I don't think this food waste is used to create compost then to recycle the phosphorus.
Yes.
Do you think that this will be a more easy way to rethink all this cycle? Because, you know, if you need to change the wastewater, the brown water system for all the city, maybe it's more difficult, but just to collect a bag is something that they are already doing. So maybe just to have a center to collect everything and create compost there makes more sense. Or maybe create compost in our home and then transfer the compost. I don't know. Do you think it's something that is more doable for our society, or still it's something very difficult?
No, absolutely. It's absolutely doable, and it's absolutely happening. So what is collected in Brussels, I mean, in Flanders for sure, and for years, but also in Brussels, it is turned into compost.
Wow, okay.
Not in Brussels, indeed. There is no system in Brussels yet, but there are discussions of exactly what to do when we will need to scale up and gather even more of this. So absolutely, you're absolutely right. It is indeed a lower hanging fruit to treat or to do something with the organic waste. It is happening in Brussels. I think things will change very soon, actually. Yes, and also, as you said, to make the compost for ourselves, or even the community compost. I don't know if you know, in Brussels, for example, that there are, in some neighborhoods, there is really a community compost with someone that is even responsible for it. And you can, let's say, register there and take your organic waste there, and then take your share of compost. And this is indeed, as I say, like the smallest and easiest way to close the loop, you know, to really make it from your house back into your pots. And it's not only good for them and for avoiding the food waste, but also it's nice because, like, for people like me, that I am a foreigner and I'm new, it's good to meet people, you know, to just say, hi, neighbor. It's, you know, and also people that you care about the same things. So all these things, they are important if we are talking about us and our lives in the city, no?
Yeah, definitely. So we have still a bit of time, but we don't have questions. So what I would ask you is, do you have some tips for us and for the audience regarding how to reduce our phosphorus waste? So how we can actually reduce the waste of phosphorus?
Yes, considering that we are not going to go tomorrow to do holes in our toilets, what can I do better?
Well, try to, as you said, like food waste is the lower hanging fruit. So making sure that, we avoid food waste, and the one we have, maybe we do something good about it. We collect it separately, or even we compost it, and so on. And exactly because we cannot start, it's not on us what to do with our poo. As you saw, when you saw like the little food that comes into our houses, there is a huge thing of flows going behind. So it matters what you choose to eat, right? So let's say, as with everything, animal products are less efficient because they need more input in nutrients in order, for less output that comes to us, again, in nutrients.
So definitely reduce meat and dairy products. It's a good strategy.
Or I would say indeed, like having a more environmentally friendly diet, which does mean reducing meat and dairy products. It's also good for nutrients and for phosphorus,
Okay.
not only for the climate.
So today we learn another things that actually is good and push us a bit more close to vegetarianism, or at least a very low meat based diet. Anastasia, thank you so much.
Thank
It
you.
was really nice. And I am would be nice if you can stay with us for the presentation for Marie, and
Of course,
maybe
I'm
you
looking
can
forward.
you maybe have questions for her after. So now we are going for a little break of 10 minutes. We are coming back at 8:30. In the meantime, we are going to leave on screen some facts, some questions regarding this last discussion that we had. We are going to also show on screen before to start again the answer of these questions, but maybe it would be nice for the audience to try to reply to the questions and see if they know something about it.
Without Googling.
Without Googling, of course, without Googling. So, of course, go to refill your glass because you need probably another beer for the second speaker. And Marie, we are coming back for you. So we are waiting for that. And so we're coming back in 10 minutes. See you later, guys, and enjoy your break.
Yeah, see you.
Here we go, guys. Welcome back for this second talk of today. Here again with me to help me with the guest we have Anna. And Anna, did you like the first talk? Was it very interesting for you?
Yes, very, very interesting.
And for all our audience, if actually you didn't have the chance to follow the first speaker, you can rewatch this live on Facebook and YouTube just after the end of the live, which should finish at 9:30. So we will be able to see also the first part of this first day of Pint of Science 2020 Belgium. As you know, unfortunately, we need to stay in this condition. But if you stay until the end, we have a big surprise, because there is also a live event in Brussels, and we still have some tickets for it. It's very cheap, but considering the measurement that we need to take, the social distancing, the physical distancing, we have a huge venue, but there is not much people that can stay inside that. So not so much space left, a few tickets, but if you want, you can join us here in Brussels. But this is going to be on Thursday, the 10th, but today we still have a speaker. And I'm going to present to you again, Marie van de Sand. Hi, Marie.
Hello.
Did you like the first talk?
Very much.
Yeah, it was very interesting. It was very interesting. And I'm sure that also yours will be very interesting. So you are a postdoc researcher, as I was saying before, at the Institute of Astronomy of KU Leuven.
Mhm.
And today you're going to talk about stars, but in a different point of view, in a certain way also philosophic, I would say,
Yes.
because in the end, it's very interesting, this approach. So without waste more time, we just leave to you the stage. We just give you a bit of time for you to prepare with the slides. If you are ready, just okay, perfect.
Great.
So, as always, for our audience, if you have questions, just shoot in the comments or wait until the end for the Q&A session. But don't hesitate to do that. Marie will be more than happy to reply. Marie, the stage is yours, and good luck.
Thank you, and thanks everyone for tuning in, and thank you, Pint of Science, for allowing me to speak in this virtual bar. You've probably heard the saying that we're all made out of stardust, and that's actually true. During the Big Bang, only hydrogen, helium, and a little bit of lithium was formed. Everything else, the carbon in our bodies, the oxygen in the air, the phosphorus that Anastasia was talking about, the metals in the devices that we're now using to communicate, all these chemical elements have been forged inside the hot cores of stars that have died a long time ago. And somehow all these chemical elements produced by stars that are now dead have ended up in this configuration, our Earth. That's quite special because, well, space is enormous and it's also quite empty. So today I'm going to talk about how we recycle the elements of dead stars into new planets. And stars are still being born and are still dying in our galaxy, the Milky Way. We just don't notice this on a day-to-day or rather a night-to-night basis because it happens on timescales that are much larger than the average human lifespan. I'm talking about billions of years rather than 8 years. So we don't really notice this. And the space in between the stars is called the interstellar medium. And it's quite empty. It's not completely a perfect vacuum, but there's not a lot of material floating around. But there are certain regions where there's these denser clouds of material, and from such dense clouds, stars can be formed. And the life and death of a star is all determined by its initial mass, so its birth weight. If a star weighs more than 8 times the mass of our sun, we call it a massive star, and these stars live fast and die young. They're very bright, and towards the end of their lives, they become red supergiants. And finally, they will die in a violent supernova explosion. And during this explosion, the star will eject all the material that has been formed in its core, all the chemical elements newly produced from lighter elements, they will be ejected back into the interstellar medium, enriching it with its life's work. The only thing that will be left of the massive star is either a neutron star or a black hole. Stars like our sun live a much more quiet life. So first of all, towards the end of their lives, they become red giants rather than supergiants. But a red giant is still enormous. So when our sun will be a red giant, the surface of the sun will lie somewhere between Earth and Mars. So Mercury and Venus will be swallowed whole, and things will be quite toasty here on Earth. But no need to worry, we still have some 5 billion good years left, well, if we behave, of course. And as our sun will die, it will also eject its outer layers. But it will not do this in a violent explosion. It will do this in a much more gentle and calm way, a breeze rather than an explosion. So a stellar outflow, gently returning all the material back into the interstellar medium. The only thing that will be left behind is a white dwarf. So by following the trail of these chemical elements as stars are born and then reintroduce heavier chemical elements into the ISM, by following the chemistry along the way, we can try to figure out where we come from. So let's start at the end. This is IRC 10216. It is a solar-like star that is currently dying. This is an image in the optical, and in fact you see many stars here, but none of them are IRC 10216. The only thing you can see of that star is the outflow, so the material that it's gently throwing back into the ISM. And those are these concentric circles and arcs. And the reason why we can't see the star itself is because dust is being formed within this outflow. But first, let me talk about the scale of this thing. So on the sky, this takes up 2 arc minutes, and this corresponds to 120 astronomical units. 1 astronomical unit is the average distance between our sun and the Earth. So that's the radius of the star at the center. And this entire outflow, this is actually only a piece of the outflow, just the thing that we see here is already several times larger than our solar system. Dying stars are enormous. We can't see the dying star because dust is formed in the outflow. And that's actually quite remarkable because the star itself is throwing away lots of gaseous atoms and molecules, and we have a phase transition. We go from a gaseous molecule to a solid state dust particle. This star is surrounded by billions of tiny soot particles. Other stars like it are surrounded by tiny grains of sand. And this dust plays a very important role to the chemistry of the interstellar medium, simply because it's so good at hiding the optical and ultraviolet light from us. This is another example. So again, an image in the optical of a very small piece of the sky. And it looks like there's a hole in the sky. There's no stars, it's just a blob without stars. Strange. I said before that the interstellar medium is rather empty, but we have these denser clouds of material floating around. And this is one of those. This is, he's called Barnard 68, by the way. And the density of gas, and especially dust, is large enough so that we can't see what's going on behind that cloud of material. If you switch to a different wavelength, a longer wavelength, we can see through the dust and see what's going on behind this star. So there's a bunch of stars behind this cloud. We simply cannot see it. And this ability of dust to shield against optical and ultraviolet light is it's very useful for chemistry to happen in the interstellar medium, because it's not easy for chemistry to happen in space. Like, it's a very hostile environment. So first of all, space is empty. I said that this is a dense cloud. So within this region, there's 10,000 to a few million particles per cubic centimeter. And that might sound like a lot, but in this room and in your room, in 1 cubic centimeter, there are like 10 to the power of 19 particles per cubic centimeter. So that's 13 orders of magnitude at least of a difference. It's 13 zeros difference. On Earth, we would call the density of such a dense cloud actually just a vacuum, a very an ultra-high vacuum. But in space, that's dense. And when you think of it, for chemistry to happen, for a molecule to form, you need two atoms that collide and meet each other, and they have to stick together for long enough for a molecular bond to form. If the density is low, it can take a very long time before you meet another atom to form a bond with. But time is on our side. Even if it takes years or even centuries before you meet another atom, you're staying in that cloud for 100,000, maybe a couple of million years. You have time. You have all the centuries that you need. The second part, second reason why chemistry in space is difficult is this ultraviolet radiation. And I think we've all experienced the effects of being exposed to UV radiation, namely a sunburn. So our sun radiates a part of its energy in the ultraviolet part of the electromagnetic spectrum. Our atmosphere filters out most of these UV rays, and still we get a sunburn, and still we can get cancer because of these highly energetic photons. Now, if you're a molecule in space, you don't have an atmosphere to protect you because you're a molecule in space. And not only that, you're surrounded by all these stars that are irradiating you from all angles. Some of them are solar-like stars, so like a few UV photons, but some of them are these massive hot stars that radiate most of their energy in the UV photon. So you've waited for centuries before you can finally form a molecular bond, and then one UV photon comes around and just breaks up your bone, gives you a chemical sunburn, breaking the molecular bond, photodissociation. So then dust comes in very handy, because dust can protect as a sort of shield against UV radiation and protect whatever chemistry is going on. So even though space is not a pleasant environment, there's still a lot of chemistry going on. And so far, more than 200 different molecular species have been detected in the interstellar medium and around dying stars. The type of chemistry that you see depends a lot on the density. So in a diffuse cloud, the density is really low, so 10 to a couple of hundred particles per cubic centimeter. So this means that there's not a lot of bumping going on, and also there's not a lot of shielding against UV radiation. So we see a lot of atoms floating around and also some simple molecules. H2 is the most abundant molecule in the universe, simply because hydrogen is the most abundant element. The second most abundant molecule is carbon monoxide. And then there's other simpler molecules that are also present, and as well as their positive ions. And these are formed when a UV photon just knocks an electron out. If you move to a denser region, there's more little guys for you to bump into if you're a molecule, and also you're shielded against UV radiation. So more but longer molecules can form, such as water, useful for living, H2CO or formaldehyde, useful for preserving things, HCl, hydrogen cyanide, it tastes of bitter almonds and is very good at killing you. But there's also more exotic molecules floating around in space, molecules that we don't see on Earth, such as C4H. That's 4 carbon atoms in a row with only 1 hydrogen at the end. If C4H would walk into this room, it would be hydrogenated in no time, because there's a lot of water in our atmosphere, the density is very high, C4H doesn't stand a chance. But in space, the conditions are just right for our C4H to survive for a very long time. Another type of molecules that we see in these dense clouds are complex organic molecules. So molecules that organic chemists or, other chemists, and maybe most of us as well, can recognize from our, not necessarily daily labs, but they play an important role, such as formic acid. So it's formed in dense clouds and also by ants. Ethyl formate smells like rum and tastes of raspberries, and methanol is the alcohol that makes you blind, also drunk, but especially blind. If you look at these molecules, they're quite complex. So there's a lot of atoms in these molecules, and we can't really there's a lot of atoms in them, and if you would only take into account gas phase chemistry, so things bumping into each other on the gas phase, we cannot form the amount of these complex organic molecules that we see in the gas phase. For this, we need our friends, the dust particles. So here I'm going to show you a beautiful animation of the Universiteit Leiden, and it's going to show you the surface of a dust grain in a dense cloud. We have these CO molecules on the surface, and the white dots are hydrogen atoms. Hydrogen atoms are much lighter, so they are able to hop around on the surface much faster than the heavy CO. And here in front, in the middle, we have methanol being formed. A CO molecule arrives from the gas phase. Some hydrogen atoms zoom along and cause more complex species to be formed. And now these two molecules shift closer together, much slower because they're heavier. And now we have, this was a formation of methyl formate, which is the simplest ester. And now two HCOs come together. We're still waiting on a couple of hydrogen atoms to hop along. And whoop, acetic acid has been formed. Looks like a tiny dog. Another CO molecule arrived from the gas phase, and now a UV photon will hit our methanol molecule. Boom, there it is, breaking the hydrogen bond, and now these two guys can come together and we have another complex organic molecule being formed. So this happens slowly, but again, we have time. And over time, our dust grain becomes covered by an icy mantle of complex organic molecules. And as our dust grain becomes incorporated into a star-forming region, it gets heated up, and this causes these complex organic molecules to evaporate. So we see the reason why we see these complex organic molecules so abundantly in the gas phase is because they were formed on the surface of the dust. The dust acts as a sort of meeting place for chemistry to occur much faster. So it shields against UV radiation, and it provides a nice meeting surface for complex molecules to be formed, things that wouldn't have been possible in the gas phase. Now, as our dense cloud becomes unstable, it can collapse and stars can be formed within the cloud. And this is an artist's impression of star formation. So at the center here, we have the protostar, the star that is currently being born. And around the protostar, there's this disk of material. The material from which it's born is an accretion disk. It's slowly falling onto the star. This disk is composed of gas, dust, and we also call this the protoplanetary disk, because this is where planets are formed. And by now, we know that planets are a very common byproduct of star formation. And the first step to forming a planet is two dust particles sticking together, because that's how you get a larger dust grain. And then you can get a tiny stone, you can get a larger rock, you can get all the way up to planets. Of course, it's much more complex, it's still not fully understood, but it all starts with two dust grains sticking together. And nowadays, observations are almost as good or maybe even better than artists' impressions. This is the protoplanetary disk around HL Tauri. It's not an image in the optical, it's taken at longer wavelengths in the sub-millimeter range. And what we here see is the emission, so the radiation coming off of dust grains. And what's especially interesting is that we have these dark bands within the protoplanetary disk. And one of the theories behind the origin of these dark bands is that they're formed by planets born within the protoplanetary disk that are orbiting around the protostar and carving their way through the protoplanetary disk, clearing the path. So what we have here is actually a sort of ultrasound of a planetary system being born around a star other than our sun. Now, the planetary system we know best is our own solar system, and this is a very zoomed out view of our solar system. So here on the left, we have our sun. On the right, we have our closest, we have our closest stellar neighbor, Alpha Centauri. Now, the main products of planet formation are, of course, the planets. So Mercury and Mars are somewhere over here. Here are all the planets. But there's also a lot of leftover material, remnants from our time in the protoplanetary disk. There's a bunch of them in the asteroid belt between Mars and Jupiter. There's also the Kuiper belt at the outer edge of our, after all the planets, and then around all of this, further away, we have the Oort clouds. And we can see these remnants as a sort of historical artifacts. By studying them, we can figure out the history and the composition of the protoplanetary disk, so the disk from which our planets and our Earth was born. Sometimes these remnants fall on top of the Earth. Most of the time that's fine, so a meteoritic impact, no big deal. Sometimes all the dinosaurs die, so it's a bit of a gamble. Other remnants are more gentle and they are distant visitors. So comets, for example, they come by either regularly every 80 years or so, like Hale-Bopp, or every 6,500 years, like Neowise, that we could see this summer. And comets are seen as a more pristine remnant of our time in the protoplanetary disk. So if we can figure out, by studying the composition of a comet, we can determine more or less how the material, the chemistry, the dynamics of our protoplanetary disk from back in the day. That's why the European Space Agency sent a Rosetta mission to meet a comet, and they met in 2014. It was beautiful. And this is the comet that Rosetta was visiting. It's called 67 Churyumov-Gerasimenko, or 67P. Now, comets are often described as dirty snowballs. This isn't a ball. It's not spherical at all. There's just two blobs sticking together, already quite interesting. And you see these jets emanating from the nucleus of the comet. And these jets are gas phase material that's just evaporating from the surface, because as the comet gets closer to the sun, it heats up, and everything that's stuck on the surface, all the icy material, is evaporated off. And I really like this sequence of observations. So this is all by Rosetta. This is the surface of the nucleus of that comet. So on the left, there's a cliff. It's a couple of tens of meters high. And you see here on the floor, on the ground of the comet, there's just a bunch of rocks lying around. We have the geography of the nucleus of that comet. All these stripes are just cosmic rays hitting the detector, but you also have these specks flying around, and you can see those as sort of like snow. So we have the geography and the weather of the comet here in this sequence of observations. I think that's pretty cool. Rosetta was able to sniff out the composition of all this gas phase material that's emanating from the nucleus. And it found an entire zoo of molecules. So there's a long carbon chain, such as methane, ethane, propane, butane, and so on. There's also aromatic ring compounds. Benzene is the simplest one. There's a bunch of alcohols, also volatile molecules such as carbon monoxide and dioxide. There's salts. There's a lot of smelly ones containing sulfur, so these smell like rotten eggs, not super pleasant. There's a different smell also, molecules containing ammonia. There's poisonous ones containing cyanide, but the king of the zoo is glycine. And glycine is the simplest amino acid. Amino acids are essential for life on Earth. So a molecule that is essential for life on Earth has been detected on a comet, where it was formed purely by astrochemical routes. So that's quite cool, especially since it feeds into, one of the theories regarding the origin of life on Earth. So one states that perhaps the necessary molecules were brought to us by meteoritic impacts. When the Earth was still young, there were a lot of meteors just bumping into it, smashing everything up. And these large rocks could have been covered by an icy mantle containing complex organic molecules, maybe glycine. It's able to form in it's able to form in our solar system, in our protoplanetary disk. So why not? Simple sugars, fats, proteins. One of the theories around the origin of life states that it has an extraterrestrial origin, so an astrochemical origin. And I would like to end my talk with this picture. This was taken by Voyager 1 as it was leaving our solar system on the 14th of February 1990. So before it left us, it took one look back and took this picture of our Earth called the pale blue dot. In case you can't find the Earth, it's right here. And this is actually a group picture of humanity. Everybody that was alive at the time is on this picture, as well as everybody that had already died. And people that were yet to be born, including myself, are also on this picture. Because all the material, all the chemical elements necessary for our existence, the carbon, the nitrogen, the phosphorus, the oxygen, the metals, they were all there. They were all recycled from dead stars into this configuration, just conglomerated around a bunch of dust particles stuck together, our Earth. Thanks for listening.
Thank you so much, Marie. It was very, very interesting and was astonished, actually. I will just leave the stage to Anna because she's probably full of questions.
I'm speechless with that ending. But I've invited my best friend Rosetta to the talk.
Oh yeah, I remember him.
But yes, so in the meantime, while we are starting with the questions, Anastasia, if you have any questions, just give me a sign with your hands and I will put you in the conversation. She's just saying no for now. But I'm sure that's something will come out.
I will ask for her which type of stars make phosphorus. I'm sure she wants to know.
Of course, I didn't look it up. I should have done my homework. I will.
But in the meantime, I will say to our audience, if you have any questions, please just drop in the comment sessions. We have a bit of time and we can abuse of the knowledge of Marie to know better about this very interesting topic. So Anna, do you have a questions or I should go with my stupid questions?
I found out it's formed in supernova. So it's formed by massive stars. Not stars like our sun. Voilà.
Okay.
The sun is not going to make phosphorus, not the sun.
No. But it does form carbon.
Yeah. And no, I mean, I could ask a lot of questions, but I'm an astronomer myself, so I think it's better if we leave the audience to ask their curiosity. Yeah.
So I will go as a biologist with my very stupid question. And so you are saying that one of the theory is that life arrived on Earth from with comets, basically.
Mm-hmm.
So since I think that around the universe there is a lot of comets, so this actually is a kind of theory that say to us that probably there is someone else outside. So there is some other civilization or a form of life actually outside the...
Yes, chances are that that's the case, simply because it's a numbers game, right? There's so many planets around so many stars, and if chemistry is universal and we can form these molecules that are essential to life on Earth, of course this is a very carbon-based life form that we're familiar with, then why not on a very similar sort of configuration of planets and the star and all the comets. But of course you need to also take into account all the chance events that happen. So if there wasn't a meteoritic impact, perhaps the dinosaurs would still roam on this Earth and we wouldn't be having this conversation. So not only do you need to form a planet and you can have all this interesting chemistry going on in space, but yeah, you need to have the right amount of impact, it's really quite, when you think about it, it's very strange that we exist. everything could have gone very wrong.
Maybe no. My point is maybe it's not unique, but it's just very rare. You know, so probably somewhere else we have this. So we have a first question from Mikael. Would the landing of the meteor on a planet be likely to break this organic molecule with the heat, especially if they are on the surface? This, I think, it's like a basic chemistry question in a certain way.
That's a possibility, of course. But then again, if you have enough meteors maybe arriving on Earth, even if it's just a piece of the complex molecule, perhaps this can start a sequence, because another theory is just that you have this primordial soup, and then just a lot of the impacts, the energy of the impacts and lightning on the weather on Earth, lots of lightning can introduce enough energy for complex molecules to form. But maybe you can sort of kickstart this process by just having some already there. It's just one of the theories. I have no idea whether it's right or wrong, but it's a theory. And in fact, all the hard work in space can be just annihilated by the impact. But maybe something is left over.
Yeah, definitely. So I go on with another question from Matteo. Thanks for the talk. It was amazing. How many of these extreme and different conditions that happens on stars during their lifetime can be reproduced in a lab?
That's a very good question, and it's quite difficult to do so. So the chemistry in a dense molecular cloud, you can sort of you can do that in a lab using ultra-high vacuum devices, and those are very expensive. But you can study reactions in the gas phase by sort of simulating a very cold environment. So it's in a flow tube. It's I don't understand how they do it. I mean, I read the papers and stuff. It's a bit weird to me that you can do all these things. It's amazing. So you can study chemistry at very low temperatures using such flow tubes. You can then pump out most of the material within your flow tube, but you can also study dust-grained surfaces by sort of making up an astronomical dust grain. And then you layer it with CO and N2 and just very common elements in a molecular cloud. And then you irradiate it and you heat it up and you see what comes off, all in an ultra-high vacuum chamber. There's only a few universities that are able to do so. And their work is very much appreciated by astronomers, astrochemists like me, that use the data that they retrieve, because you really have to go to these extreme environments, because it's not room temperature, it's not 1 atmosphere pressure. Chemistry does weird things in such environments. Like, everything can be super weird, but you have to know. And thanks to great laboratory chemists. And also computations. You can use quantum chemistry, but that takes time and computing power.
Yeah, that for now we don't have. So we are waiting for quantum computers, and once we have it, everything will be.
That would be nice. That would speed up
easier, definitely easier. We have another question. You say that life in Earth is carbon-based, but could it be that somewhere else life could be hydrogen or phosphorus-based? This is a classic question, actually.
Yeah, that's possible. Hydrogen-based seems a bit unlikely to me, because it's just 1 proton and 1 electron. There's not a lot of things that can go on if you can't really form a long hydrogen chain. You can do the same for carbon. But for example, silicon is also very abundant. So now we are very carbon soot-based, but silicon also has 4 bonds, for example.
I think that Asimov wrote a book imagining a creature silica-based, basically, silicon-based, basically. So it's probably something that maybe is there outside. We don't know.
But it's very difficult to imagine, because we are so carbon-based.
Indeed. It's very, very difficult. It's very, very difficult. So we have another question from Tanin. There is another girl of Pint of Science, but I will just read from the other chat. Are there elements that can exist in space, but that we on Earth cannot find or create ourselves?
Everything everything on Earth has come from a star. There's probably some very radioactive species. I think Anna knows more about that. Some species that have a very short lifetime, simply because they decay. And on Earth, we maybe do not have more of those, but I'm not entirely sure. In fact, we have, so at the end of the periodic table, there's these, like at 114, the Latin names, these are they only have been formed on Earth. Because we have to, they've only existed for a very short time, not even a second probably, and they were formed in an accelerator just by knocking things next into each other and see what sticks. And those are not in space. So it's rather the other way around, because everything on Earth comes from space, but on Earth we can, I don't know, do crazy things and just knock things into each other and create new elements that, nature doesn't waste its time on.
Yeah, I think it's possible that some elements, we have them in more exotic form, like, for example, very neutron rich, that in Earth we cannot bombard them with enough neutrons to have them stable. Or that, as he said, that they are unstable and you can only observe them while they are forming, basically.
Yeah, thanks.
I actually want to know, Marie, which is your favorite chemical element or your favorite molecule?
My favorite, it's during my PhD, I was very into hydrogen cyanide. No, cyanopolyenes. I forgot their names already. It's been a while since I studied them. So that's H, and then a couple of carbons, and then at the end, so HC3N, HC5N, HC7N. You can't really find those on Earth. You have to make it, it's possible to make them in a lab, but not a lot of labs want to do that, because for that you need hydrogen cyanide, and hydrogen cyanide kills you if you don't watch out. So it's difficult to study, but those, I like those guys. They're just long chains. Yeah.
So I will let Anastasia to jump in, because she has a question for you, Marie.
Okay, thanks.
Hi, Mary. Thanks so much. It is great. I always feel a bit stupid, but Anna tells me I can ask whatever.
Of course.
Exactly. So, we discussed about the stars that, they're born to die, and the planets born, but do planets die, actually?
Well, the fate of a planet so Mercury and Venus, they will be swallowed whole by the sun. But for example, our Earth, maybe it's not swallowed whole, but we can actually see, there are observations of such like stars like IRC 10216, so solar-like stars that are dying, and where we have a companion circling them. And for one of them, it's called L2 Puppies, in case you want to look it up. It's a very beautiful observation, where we see the star and there's a disk of material, and surrounding that disk there is a companion, which could be a leftover planet. So faraway planets, they're probably safe, but and then they will circle around the white dwarf, but life is not possible anymore. So the close by planets, they get eaten up by the star. The ones a bit further away, they can distort the star and cause the outflow not to be spherically symmetric, but have, for example, a spiral or a disc or an hourglass shape. And then the ones further away, they will, I think they just will be space rocks.
So basically, we can only talk about like planets and have planets in combination with a star.
Yeah. Yes.
It's part of the definition, basically.
Yeah. In order to form a planet, you first need to form a star, because that's how you get a disk. Like, it's all this material falling into each other, and it's a byproduct of star formation.
Regarding this, actually, Tanina has another question. So the more stars die, the more planets we have, in theory, or it's just not very true?
The more stars die, the more the chemical complexity of the Milky Way will increase, because there will be more carbon, more oxygen injected, and maybe more planets will exist, but they will be either swallowed up whole by the star, but also perhaps that's something that I just thought of also regarding to your question, Anastasia. If there's a shock wave from a supernova passing by, perhaps the planet cannot withstand it. Perhaps, it's just an enormous dust particle inside of a cloud. But I actually don't know what happens to these planets. That's a good question. I'm going to think about that.
And actually, I have another question, which is mainly sci-fi based. So, a long time ago, I read a book from Michael Crichton called Andromeda. And in this book, he imagined that with a meteor that arrived on the Earth, inside this meteor, there is a pathogen agent that is able basically to create in human body instantly the complete aggregation of the blood. So basically you die because the blood became solid. So to be more very, very fantastic. But so I know that there are some theories on the fact that it's easier to get it will be easier for us to get in contact with extraterrestrial life if this extraterrestrial life is very simple. So like a virus or a bacteria or something like that. So do you think that this is possible considering all these theories? So it's just sci-fi stuff, or is something that actually can happen? The fact that in a meteor, in a meteor, or in a comet, you have the formation of life, not just because we know that we have some bacteria that are able to survive in extreme conditions. So maybe they might survive also there. They might create, or is too complex to have this kind of stuff?
Well, I'm not sure. That's more astrobiology than astrochemistry. But indeed, you have these extreme species, these bacteria, and like there's a little, looks like a tiny bear, but it's able to survive everywhere. But for that to happen, I mean, if you have time and everything goes
probably
fine.
The problem is that there is no water there, or at least no water in liquid form. So maybe this is why you cannot form life. But this is probably a dogma that is from traditional biology.
Yeah, that's what we need for life, right? Water.
Yeah.
So I'm not sure. It's a good science fiction plot.
No, exactly. But it's
but there's a lot of toxic material in space and floating around on these comets. But then again, like for example, hydrogen cyanide, it's very toxic to humans. And I say that it's abundant, but if you would put it in a tiny pile, but if you would put it in a tiny pile, it wouldn't be that much if you would take the yield of a comet of the things that will kill you and the things that smell like rotten eggs. It's not that much. It's mainly CO, which is also not super fine for us, but whatever, you open the window. And the most abundant ones are the most boring ones, so to speak. So we shouldn't be afraid for a bunch of hydrogen cyanide to drop on our faces.
Okay, that's definitely clear. I think there was another question from Tanin that maybe I lost in this. Is it true that you can see stars that are currently dying, but their demise is still not witnessed from where we sit on Earth? So I think this just can we see stars that are dying from here, but actually they are already dead a long time ago?
Yes, that's possible because, it takes some time for light to travel to Earth. Light is very fast, but it has a finite speed. So, for example, the star that I showed you, IRC 10216, it's one of my favorites as well. That's why I'm always saying his name. We see what was going on a couple of 100 years ago. We don't know what is going on with that star right now. We can only look into the past. We have to wait for the light to reach us. And the further away a star is, the longer that will take. So we're actually only studying the past. And the further away your object, the longer ago you're looking at. So it could be that these stars are already dead. It could be. We don't know. We're limited by light.
But can we predict actually when a star is going to die and observe that? Or we already did it, actually? I don't know if we already did the observation of a star that is dying.
Well, there's supernova explosions that go off, and then you just see, well, a detector sees that all of a sudden a bright star appears. But that's, again, a supernova explosion that happened a while ago, because we see the light reaching us. So if it's 100 light years away, that happened 100 years ago, and we just only now see it. But we can use, just by theory, by looking at all these stars, and we have, well, people were able to devise stellar evolution models. So you know roughly like, if a star is that large, if it weighs that much, it's only going to live for that long. So for example, we know that our sun will have like 5 billion years left. So because we know its mass, and we have seen other stars like that in our galaxy and in other galaxies as well, doing their thing.
Yeah. Okay. Thank you so much, Marie. It was very
You're
interesting.
welcome.
I'm afraid that our time is finished. So first of all, I want just to say thank you to Anastasia and Marie. We are going to take the last 10 minutes just to advertise for the next event. But in the meantime, we can just release you so you can go and continue with your study, or just have another beer or dinner or wherever. So for now, I'm just going to ask Anna and the other guys in the background, in the backstage, to just remove you from the screen. But please don't leave it, because after the live, we are going to chat a bit, just the team with us, to say thank you again. So thank you so much. I think the audience appreciate a lot your talks. And I hope that we are going to see you again in Pint of Science, maybe in a bar with a real beer in front of us. That would be very nice.
That would be great.
That would be very great. So Anastasia, Marie, thank you so much, and see you next time. Thank you so much.
Bye-bye.
Bye.
And then for the last wrap up, guys, I just want to advertise for the next event. This was just the first night of Pint of Science 2020. Tomorrow we are going to have another live event on Facebook and YouTube about our body from brain to guts. We are going to have a first talk about the importance of a good sleeping night. And then we are going to talk about bacteria in our guts. So we are going to speak about something very complex, our brain, and how it's very important that we sleep in a healthy way. But then we are going also to talk about all of the bacteria that lives in our body, on our body, inside our body. So something very, very interesting. And for this, of course, you don't need to book anything. We just see each other here again tomorrow at 7:30. Of course, we always push you guys to make questions, ask stuff, and whatever you want. Or actually, if you want to suggest a speaker, or if you want to come and speak in one of our events, you can do it. Just contact us through our Facebook page, will be more than enough. In October, we will probably continue with Couch of Science, our spin-off that born here in online event, and is probably going to continue. But then actually the big surprise is that we are going to have another event for the 10th, so this Thursday, that will be live from La Tricoterie in Brussels. And probably there will be a very nice event and very interactive. It will be mainly related to social science and everything related, smart cities, environmental friendly cities. It's something very interesting. And there will be also a part where you can actually interact with our speakers, and you can share your idea about a greener city. For this, you just go in our website and you can find the way to book your ticket. I will ask to the guys in the background, in the backstage, to put the link on the comments if it's possible. Of course, if you want to stay updated on all our events, you can follow us on Pint of Science Bay, on Instagram, on Twitter, on Facebook. We're always going to communicate what we are going to do in the future. And of course, this live that you just seen, if you arrived too late and you want to, or you want just to see it again because they were very, very nice, you can do it in our Facebook page or in YouTube. They are going to be online just at the end of this broadcast. So they will be accessible for all of you whenever you want, and share with your friends, with
Yes,
your
please share it
parents,
with your friends.
share with everybody. Let people know that Pint of Science Belgium is still here, even though this year was quite weird. But anyway, something good came out with this format, and we had a lot of speakers during the year. And again, so we see each other tomorrow. As always, I want to say thank you to the guys in the backstage. Thank you, guys, to Michael, Matteo, Renata, and Tanin. Today they were with us, even though if you didn't see them. And thank you to Anna. Thank you so much, especially with the help with this space talk, where actually I'm very, very bad about it. And what else? I think I said everything. We are a bit before the end of what we planned, but I think it's a good point. So, guys, I hope that you're enjoying everything. Thank you so much. Thank you again to Maria, to Marie, and Anastasia, and see you tomorrow, same time, 7:30.
Tomorrow.
Thank you. Bye, bye, guys.
Bye.